Alright. Section 3.1 is on page 103. Talks about homogeneous equations with constant coefficients. This is, chapter 3 is really the same thing over and over. You want to get the first section out, it repeats in section 3.3, 3.4, 3.5, and builds on all the way throughout. So, many second order differential equations have the form f of t. You have an independent variable y and a derivative. Equation 1, that's one right there, is said to be linear if f has the form, this function right here depends on g of t, a derivative of y and a y. And equation 1 becomes py double prime plus q prime y plus ry equal g of t. This is a second order linear differential equation. What we do, we divide by p of t, and the above equation becomes, and here it is, ready, a 1 times y double prime plus some different p, lowercase q and lowercase g. So this is really what we're going to use. We're going to make sure that's a 1 before we proceed. And given initial conditions, you want to make sure that those are the same in this class. That's ODE. And in partial differential equations, those will be different. We're going to touch on that toward the end of class. If g of t, that's this case, equals 0, we say this equation is homogeneous. So all what a homogeneous means is that this forcing factor or term is actually 0. We don't touch on that not being 0 until section 3.5. Now, this is what was discovered. I want to solve this equation. And somebody said, well, hey, that's a separable equation, and of course they are right. And if you separate and integrate, and y would equal e to the negative pt plus c, which is c e to the negative pt. That's the solution to this first order linear homogeneous differential equation. Somebody came in and said, look, if you see a linear homogeneous differential equation, linear, they didn't say of first order, of any order. They say, let y is the solution, equal e to the rt. Then, if I look at this equation, y prime is r e to the rt. So r e to the rt plus p, and y is actually e to the rt equals 0. Factor e to the rt out, you'll have r plus p equals 0. We know that e to the rt cannot equal 0, so it must be that r plus p equals 0, or r equal negative p. And if you take my assumption and say y equal e, and instead of r, put a negative pt, and just give it a constant, that will work. Well, look at this and look at this. Now, by the way, something that they're going to ask for, this right here is called the characteristic equation. Characteristic. Okay, I could do better than that. This right here is called the characteristic equation. A big deal. Something that we're going to be looking for in every problem in this chapter. And what's the catch? Linear homogeneous differential equations. So, if I look at the following theorem, this is what it says. it says given a second order, and in chapter 4 we deal with third, fourth, and fifth order. Given a second order differential equation that looks like this. The goal is always to make sure that's a 1, right? With constant coefficients a sub 2, a sub 1, a sub 0, a sub 2, a sub 1, a sub 0. If the characteristic equation has n distinct roots, since it's a second order, you're dealing with a quadratic. If the quadratic has two roots, r1, r2, we say that e to the r1t, e to the r2 are linearly independent. You all know what that means because you took math 10. Solutions of the equation. And the general solution looks like e to the r1t, e to the r2t, times some c1 and c2. And that's basically it. So let's look at the first problem. I'm looking at page 109. It says find the general solution of the differential equation. What are you doing here? You're doing what you did in calculus, except you are undoing a second derivative. Here they're saying find me a y so that if I take 2 times that y plus 3 times its derivative plus the second derivative, I'll get a 0. Since this is a linear, homogeneous differential equation, I'm going to say let y equal e to the rt. And what I need, a derivative of y and a second derivative of y. Well, I know y prime is r e to the rt, and y double prime is r squared e to the rt. So here I'm going to plug in what I have. This for this, this for this, and this for this. I'm looking at r squared e to the rt plus 3 times r e to the rt plus 2 e to the rt equaling 0. If I factor e to the rt out, if I factor e to the rt out, I'm looking at r squared plus 3r plus 2 equaling 0. E to the rt can never equal 0. So this is r squared plus 3r plus 2 must equal 0. R plus 2 into r plus 1 must equal 0. R equal negative 1 and negative 2 would be the solution. So first things first, e to the negative t and e to the negative 2t will be the actual solutions. And the general solution, according to this theorem, is y equal some c1 times e to the negative t plus c2 e to the negative 2t. And it doesn't matter where c1 or c2 go. You could swap those if you want. If they gave us initial conditions, we find c1, c2. If not, we're done. The first batch of problems, 1 through 6, they say just do that. Again, I noticed that this is a linear. We all know what linear is. Homogeneous differential equation. So I'm going to let y equal e to the rt be the solution. I need a derivative and a second derivative. Y prime is e to the rt times r, and y double prime is e to the rt times r, which is r squared. So this is r squared e to the rt plus 5r e to the rt equals 0. So if I factor e to the rt, I'll get r squared plus 5r equal to 0. And we know that e to the rt can never equal 0. This is so annoying. We know that e to the rt can never equal 0. So it has to be that r into r plus 5 must equal 0. R equals 0 or negative 5. So I know that e to the 0t, e to the negative 5t would be the solutions. And isn't that a 1? So my general solution is y equals c1 times 1 plus c2 times e to the negative 5t. That's the general solution. If I look at number 6, well, we're doing it again. This is a homogeneous linear differential equation, right? Same deal. I'm going to let y equal e to the rt. I need y prime, that is r e to the rt. I need y double prime, that's r squared e to the rt. R squared e to the rt minus 2r e to the rt minus 2e to the rt equal to 0. Factor e to the rt out. R squared minus 2r minus 2 equal to 0. So e to the rt can never equal 0. It has to be that r squared minus 2r, and since this doesn't factor, actually let me do it in 2 steps, that's okay. Minus 2 equal to 0. R squared minus 2. You could use quadratic formula. I'd rather use completing the square. Take half of the middle number and square it. That says r minus 1 squared equals 3. So here I am getting r minus 1 equal plus or minus 3. Wait a minute. Oh, radical 3. I'm sorry. And r will equal 1 plus or minus radical 3. So e to the 1 plus radical 3t and e to the 1 minus radical 3t will form the solution set, and the general solution would simply be y equal c1 e to the 1 plus radical 3t plus c2 e to the 1 minus radical 3t. That would be the general solution. The next level up is for you to find c1 and c2. Same thing as what we just did, except now they're giving us initial conditions. This is a homogeneous linear equation. I'm going to let y equal e to the rt be the solution to this. Y prime is r e to the rt. Y double prime is r squared e to the rt. So this is r squared e to the rt plus 4r e to the rt plus 3e to the rt equal to 0. Factor e to the rt out. That will be r squared plus 4r plus 3 equal to 0. E to the rt can never equal 0. It has to be that r plus 3 into r plus 1 equals 0. That makes it r equal negative 3 or negative 1. So the solution set is e to the negative 3t e to the negative t. The general solution is y equal c1 e to the negative 3t plus c2 e to the negative t. But now that they gave me initial conditions, it says y of 0 is simply c1 plus c2, and that's a 2. And y prime, if I take a derivative of this, what would I get? If I take y prime, isn't that negative 3c1 e to the negative 3t minus 2c2 e to the negative t? Where did the 2 come from? Just minus, right? And if I plug 0 in, y prime of 0, that is negative 3c1 minus negative 3c, oh boy, this is 2. Oh, that's where the 2 was. And that equals a negative 1. So I'm trying to solve this system of equations. I'm trying to solve c1 plus c2 equal 2 and negative 3c1 minus c2 equal negative 1. If I add those, I'll get negative 2c1 equal 1. c1 is negative 1/2. And now if I go to equation 1, let's see. Oh boy. Hitting the keyboard by mistake. I'll get negative 1/2 plus c2 equal 2. Negative 1 plus 2c2 equal 4. 2c2 equal 5. c2 equal 5/2. So y equals c1 negative 1/2 e to the negative 3t plus 5/2 e to the negative t would be the solution to this differential equations. you don't need to graph, just find the solution we did. Sketch the graph, you don't have to do, but describe the end behavior as t approaches infinity. What's the limit as t approaches infinity of y? That will approach 0, and that will approach 0. Y would level off next to 0. Right? That's called convergent. But that's all you have to find. Your homework on this section is on page 109, number 1 through 11 odd. I was going to do one more, but, time's running out.